So let us suppose two numbers, okay, and let us produce all the linear combinations for those two numbers. Suppose the two numbers are 15 and 12, and we know the GCD of these two numbers is 3. So let us produce all the linear combinations for 15 and 12 first, okay. So linear combinations are going to look something like this. Okay, so the A is 15 and B is 12. So all the possible values for X and Y, let's take them, and that will give us linear combinations of these two numbers. So I think I said all, but I meant to say most or some. So first, this if this is going to be 0 and 0, the X plus by it's going to be 0, and if this is 0 and 1, this is going to be B, which is going to be 12. If this is going to be 1 and 0, this is going to be 15. And if we take 0 and minus 1, this is going to be minus 12. Similarly, if we take 1 and minus 1, this is going to be 3. And if we take minus 1 and 1, this is going to be minus 3. And if we take 2 and minus 1, it's going to be 18. And please correct me if I'm wrong. And if I'm going to take 1 and 2, and it's going to be 39. And if you produce all these linear combinations of these two numbers, it is going to produce a set. Let's call this set. Yes, so this set has all these numbers. Okay, so we can see that in this set the minimum number we can produce is actually 3, which is equal to the GCD of these two numbers. Okay, so while we are making linear combinations of two numbers, the minimum number we can produce as a linear combinations is going to be equal to the GCD of these two numbers. And the identity that produces, and this identity X and Y, okay, which produces the GCD is going to be known as Bezout's identity. The Bezout's lemma goes something like this, that if you can divide a number, okay, if you can divide a number by a certain number, if you can divide, suppose D is a common divisor, okay, it's not the greatest common divisor, but it is a common divisor for A and B, then Bezout's theorem tells us that this D can be produced as a linear combination of this A and B. So let us dive further and look what's actually happening and why we can produce. So let us dive further and look at why this is happening. Okay, so if you look at 15 and 12 as numbers, when we know this GCD is 3, so we can divide 15 and 12 in equal blocks of 3. Okay, so this 15 can be divided into 5 blocks of 3. Okay, so you can see we can divide 15 into equal blocks of 3, and also 12 can be divided into equal blocks of 3 too. Okay, so think about adding these two blocks. Okay, so we are going to produce something like, if we add 15 and 12, we are going to produce something like this. What, this is going to be our 15, and another 4 layers is going to be our 12. So this is only going to be 3 into 1 2 3 4 5 6 7 8 9. Okay, so if we add 15 and 12, which is going to give us 27, this is also can be divided by 3, which is going to be 27. So this behavior follows, because what you are doing here is you are only adding these chunks of 3. Okay, and if you are going to even subtract, all you are going to do all the operations are going to occur in these chunks of 3. And I think it is very important to remember that, okay, that no matter what you do, these chunks of 3 will survive. So the very idea of the set of linear combinations having the GCD as the minimum element is this. But you can see that this can not only be described as a multiple of 3, but we can consider this as a multiple of 1 2, right? We can write 15 as something like this. 15 and 12 also can be written as this. So this can also be divided into chunks of 1, right? Because 1 also divides both 15 and 12, and 1 is also a common divisor to both 15 and 12. Okay, so how do we prove that the 3 is the minimum? Okay, so this can be actually proved using some mathematics. Okay, and the proof for Bezout's standard proof for Bezout's lemma goes something like this: that let us suppose that there is another minimum which exists in this set. Okay, let us suppose that D is a minimum from the set S. Okay, where S is going to be set of linear combinations for A and B. Okay, and let us consider that AX and BY is 0. Okay, and X and Y belongs to Z. Okay, so we are only considering the linear combinations which are going to be greater than 0, and our X and Y are going to be integers. Okay, so let us suppose that D is a minimum element from this. Yes, so we are going to prove that this D is actually going to be GCD of A and B. Okay, so how do we do that? So if D is going to be minimum of S, then D will divide A and D will divide B, first of all. Okay, so if we are taking a minimum from this set, okay, so if you look at this set and if we take a minimum from this set, okay, that minimum is going to divide both A and B. So from the figure we know this happens because all we are doing is adding the chunks, okay, the chunks of the common divisors, and we can produce those chunks of common divisors. So if you look here, and we can prove this mathematically as well by this. Okay, so let us suppose D is going to be a minimum of S, then we know that D is going to divide A and D is going to divide B. So D is a common divisor of both A and B. If this isn't the case, suppose D doesn't divide A, then we know by division theorem that if this doesn't divide A, then D is going to be, so sorry, A is going to be something like this. Okay, dq plus r. Okay, that is that when you divide D by A, this is the quotient and you are going to produce some remainder. Okay, and so A is going to be dq plus r. Okay, or you can write it as A minus r is equal to dq. So we have A minus r is equal to dq if what we know isn't going to be 3, then this is going to be A minus r is going to be dq. Okay, so we know that D is a linear combination of A and B, so we have something like this. Now if you multiply by q on both sides, we can produce something like this. And let us, this value and this value is equal, so let us substitute, and when you solve this, you can get something like r is equal to A 1 minus q x naught plus B minus q y naught. Now you can compare this formula as So R is going to be a linear combination of both A and B. Okay. Now we know that here this R is strictly less than D. Okay. So R is greater than 0, greater than equal to 0, and R is going to be less than D. We have this, and then we have R is a combination of AX naught and BY naught. AX dash and BY dash. Okay. But we have supposed that D is going to be a minimum from this set. Since R is a linear combination of A and B, R is going to belong to S and R is going to be less than D. So D isn't going to be a minimum from this set. Yes. Okay. So what we supposed contradicts. So by contradiction we can prove that D must be a minimum. D must divide both A and B if that is going to be minimum. So what this look like? What this looks like is that, let's suppose 7 and 5. Okay, so they can be divided into chunks of 1 since they are primary numbers. Okay, so we are dividing 7 and 5 in chunks of 1, and the GCD of 5 and 7 is going to be, sorry, is going to be 1. Okay, two prime numbers or two numbers who don't have a common divisors are going to have a GCD of 1. So the set of linear combinations of 7 and 5 is going to produce something like 1, 2, 3, 4. Okay, so I am trying to make parallel between this and this. Okay, so what we have done here is that we suppose a minimum from set S. Okay, then we theorize that D divides A and D divides B, and if this doesn't divides, suppose this happens, because if this doesn't divides, then D isn't going to be a minimum from set S. That's why D divides A and D divides B. That is what we theorize, and what it looks like is that if we take two numbers 7 and 5, the GCD is going to be 1 and the set is going to look like this. So if we don't take a GCD as minimum and if we take a certain another number as a minimum, suppose this is going to be D and we theorize that this D is the minimum, so we must now prove that this D actually divides both of these numbers, but we know that this 2 isn't going to divide both 7 and 5. Okay, so if we try to break this down as chunks of 2, oh sorry, I drew 8 here, so let me minus 1. So if we try to divide this 7 as chunks of 2, 1 2 3 4 5 6 7 as chunks of 2, then a remainder remains. Okay, and from here we know that this remainder is actually going to be a linear combination of A and B. We know that this exists in this set. Okay, so we failed in our job to take a minimum from this set. So this proves that if we are taking a GCD, then it is going to be a common divisor for both of these numbers. Okay, so that proves that if we are taking a GCD from the set, then that must divide both of these two numbers. But it always doesn't happen that the divisor that you take might be GCD. Okay, suppose for 18 and 12 you can divide them into chunks of 3 or 6. Since the GCD is 6, I'm trying to divide it in chunks of 3 so you can visualize it more. This is going to be 3 6 18, right? And 3 4 so this is going to be divided into chunks of 3, and this is going to be 3 into 4 12. So what we can do now is that if we look in this set, all right, if we look in this set, all right, the GCD of 18 and 12 is going to be 6. Okay, but a divisor exists smaller than 6 that can divide both of these two numbers, which is 3. Okay, so these are actually chunks of 6. All right, they are chunks of 6, but they can also be can be thought as chunks of 3. Okay, so we proved right now that if we take a minimum, then both of the numbers must be divided. Okay, but we can see here that this 3 is also going to divide both of these. But the question is, does this 3 exist in this set? Yes. Okay, so does this 3 exist as a linear combination of 18 and 12? And the answer is no. The answer is no, because whatever you do, we are always going to produce a multiple of GCD, that is 6. We can't produce 3 because 3 isn't a multiple of 6. Okay, if you try to add these chunks or subtract these chunks, multiply then add, or multiply then subtract, we are always going to be produce chunks of 6, and we cannot produce chunks that are smaller than 6. And even if it is either 0, then it is going to be 0, but if it is negative, the modulus is always going to be a multiple of 6 here. Okay, so what remains now is we have proved that if we take a minimum from this set, it is going to divide both A and B. So what remains, so what we proved is the D, which is minimum from the set S, is going to be a common divisor of A and B. What remains is to prove that this is actually GCD. So we can prove this as follow. Let me take a new paper. So we can prove this as follow, right? So suppose there is another number C which divides both A and B. Okay, so suppose there is a number which divides both A and B. Then since it divides A and B, it is going to divide all the linear combinations of A and B, and this map back to the block figure I shown earlier. Okay, if we are going to produce a combination of those two numbers, it is always going to be a combination of a factor of those two numbers. Okay, or you can see it is, if C divides A and B, then whatever linear combinations of A and B you produce, it is going to be divided by C. Okay, so if these are two numbers which can be divided by 3, and if you are going to produce some combinations of these two numbers, it is always going to be divided by 3. Okay, this is divided by 3, this is divided by 3. If we produce combination of these two numbers, it is always going to be also divided by 3. So that is what I wrote here. If let us suppose there is another common divisor for A and B, then we know that it is going to divide both. So let us suppose there is another common divisor, so it is going to divide both A and B and all the linear combinations of A and B. Now since this divides all the linear combinations, we know that our D is going to be some combinations of A and B too. Since it is going to divide all the linear combinations, it must also divide D. Okay, but we also know that D also divides A and D also divides B, that D is a common divisor of both A and B. So we also know that D is also going to divide all the linear combinations of A and B. That is to say that D is going to also divide C. So we have a condition where C divides D and D also divides C. So what that means is C must equal to D. So what I proved now is that if we have a common divisor, okay, if we have a common divisor, then it is automatically going to be equal to the minimum divisor of those numbers, okay. And this proves our theory that the minimum we can produce as a linear combination of A and B is always going to be the GCD, okay. This proves that D is equal to GCD.